Okay, so we'll get started. So thank you all for coming. This is Zero to Trajectory Tracking using the FRC 2020 software. My name is Pratik and I am the president of Team 5190. I've been with the team for 2 years now, going into my last and third year. So let's get started by talking about today's outline. So we'll do a really quick introduction to what WPILIB is. And then we'll talk about trajectory tracking and why we're actually doing all of this. Then we'll actually program that robot to track a simple trajectory, and we'll test and tweak our code. So are any of you programmers on your team? So what languages have you programmed in?
We just use Java.
Java, yep.
Python.
Python. Nice. So it looks like all of you have been using typed languages. So this presentation will focus mainly on typed languages. So we'll be using Java for this because a majority of teams use Java. So what will you learn today? You'll learn how to write a simple Java program if you don't already know how to do that. And we'll make it track a trajectory in the autonomous period. You will learn about the motives behind trajectory tracking and why we're actually doing something like this during the autonomous period. And you'll learn how to write all of that code using the new libraries. So we'll actually program live in all of this, but you shouldn't really take out your laptop or write down the code because all of this will be available on GitHub, and we'll be posting a link to this video online as well. So it's more important that you look and understand the concepts so that you can program it yourself when you go home or to your build space. So the links are all over there. I'll have them at the end of the presentation as well. So what is WPILib? Does anyone know what WPILib is?
It's essentially just an API built for the FRC robotics competition programming and stuff. So it's already pre-made, so like you use it to program robotics.
Yeah. So WPILib, as you said, contains all the core libraries to program things on the robot. So you can program things like encoders and motor controllers and things like that. And the nice thing about WPILib is that it's largely community driven. So there's developers all across the US who contribute code to this library. So what can you actually use this for? So you can create Java or C++ programs. So as I said earlier, we'll be using Java for today's workshop. There's an entire series of classes, and they come together in a thing called command-based programming. So this makes it really easy to set up autonomous routines and things like that. And you can program motors, encoders, PID controllers, and things like that. So what we're going to do first is we'll write a simple robot program. So we'll start with a robot class, and we'll create our drivetrain subsystem. So this robot right here is what we're going to be programming. So this robot has 4 motors. So we're going to create the 4 motor controllers. And we'll talk about the master and follower configuration. And we'll also talk about reversing motors on one side. So we can get started. So I've created using VS Code, I've created a basic robot program using the time skeleton. I'm not going to show you how to create a project in VS Code because there's a lot of documentation already available for all of that. So I've opened up the project in IntelliJ because this is what I use to program Java robot programs. So you can see that we have a simple robot class right here, and there's nothing in it. So the first thing we want to do is actually create our subsystem. So we're going to create a new package. Laptop's not cooperating today. So we'll create a new package called subsystems. And in there we'll create a new Java class called drivetrain. So every subsystem that you write in your code will extend a class called subsystem base. So this is part of the command-based library. So we'll extend subsystem base. And in here, we're going to start with initializing our hardware. So this robot has 4 Neo motors on it. And with Neo motors, we're using the Spark Max motor controller. So we're going to create 4 of those. Now it doesn't matter what motor controller you're using. You can use Talons or other Sparks or Victors or things like that. Because in the end, all we're going to be doing is giving some voltage to the motor. So let's create our 2 master motors. So we can say can Spark Max left master. And the first parameter is the ID. So the ID for the left master on this robot is 1. And we're using brushless motors. So semicolon. And then we'll do the same thing for the right master. And the ID for that is 3. And now we'll initialize our slave motors. So and the ID for this is 2, so brushless again. And finally, the right slave motor. Now what we want to do is actually make the slave motors follow the master motor. What this means is that when we give some voltage or some command to the master, we want the slave to exactly mirror that command. So we can do all of this in the constructor of this class. So we can create a constructor. And in here we can just say left slave dot follow left master and right slave dot follow right master. Now there's one more thing that we need to do. So if you think about it, when the motors on the left side of the drivetrain spin clockwise, the robot on the left side moves forward. But when the right side motors spin clockwise, the right side will move backwards. So when you give motors positive voltage, they will spin clockwise. So in that case, if we give our left side and our right side positive voltages, the left side will move forward, but the right side will move back, which means that our robot will spin. We don't want that to happen. So that means that we need to invert the right side so that when we give it positive voltage, so let's say 6 volts or something like that, the right side actually moves forward. So the way we do this is we can say right master dot set inverted to true. So that will basically invert the right side. And just as a safety precaution, we also set the left master to false. So now we have created our drivetrain class. All we have done is initialize our hardware. At this point, do you think that we can drive around or follow any trajectories? Why not?
I don't know. Well, first of all, you gotta actually initialize it in your actual code.
Right.
It's just like creating the subsystem. You gotta go into the robot code itself and actually call it. So.
Yeah, so we haven't written any code to actually set speeds, and we actually haven't instantiated this class. So where we store all our subsystems is in a class called the robot container. So let's create that class. And in this class, we can actually create an instance of our drivetrain. So we can say drivetrain, and we can just call this drive equals new drivetrain. So we have created a robot container class, and we've created our drivetrain inside of this class. Now, we still haven't initialized our robot container. So now let's go to our main robot class. And up here, we can create a robot container. And then when our robot is initialized, we can actually initialize the container. So when this is called, it will initialize our drivetrain, and when we construct our drivetrain, it will do all of this. So it will set our slaves to follow the master, and it will set inverted on the right side and not set inverted on the left side. So that's your basic drivetrain, setting up the hardware and things like that. So this doesn't do anything yet. So let's go back here. So let's talk about trajectory tracking. Does anyone know what this means? What it means to track a trajectory, or path following is another term for it. Does anyone know why it's used or what even it is? Yeah.
Would it be like measuring how far the robot has traveled and in what direction so you can navigate the environment autonomously?
Kind of. So yes, it uses a lot of field measurements. So it's essentially you draw some curve from point A to point B on the field, and then you follow that curve essentially. So why do you think path following is important in the autonomous period? Why don't you just drive forward, stop, turn 90 degrees, and then move forward again? Why is it so important?
Well,
Yeah.
it could be like, it's like really smooth instead of like, you know, like individual steps. Like it's the ability to do things really quickly and, you know, much more faster.
Yeah, so trajectory tracking is usually a lot quicker because you don't have to really stop along the way, and oftentimes it's actually more accurate. So trajectory tracking has been a large part of the autonomous period through several games. A lot of teams have been using trajectory tracking during the autonomous period. So we'll take a look at a few examples of teams that have been using trajectory tracking in the last couple of games. So we'll start with the 2017 game, and I want you all to focus on the bottom left corner robot when I start the video.
3, 2, 1, go!
Here we go, folks. Autonomous action now. Robots operating from pre-programmed instructions. And already it's a...
Alright, so can someone tell me what that robot did during the autonomous period? Yeah.
It placed a gear on the side of the airship, and then it aligned itself with the hoppers, grabbed all the balls that fell out, and shot them into the pipeline.
So did you notice anything about the way it got to the airship or the way the robot came back to the hopper?
Smooth motions.
Yeah, so it followed a series of smooth motions. So this is just an example of the first trajectory. So they started near the Alliance station and followed a smooth curve to place the gear on the airship. And that's the reason that they were able to do so much during the autonomous period. They could place a gear and shoot the fuel into the boiler. Let's take a look at another example, this time from 2018. So this time you should focus on the center robot on the right side. Alright, so can someone tell me what happened in that video? Yeah.
They put a cube in the switch and 2 on the scale.
Yeah, and how were they able to do all of that in 15 seconds?
With basically following nice curves instead of stopping and turning.
Yeah, so they were able to follow a series of nice and smooth trajectories in order to get all 3 cubes during the autonomous period. So they started here, followed a smooth trajectory to the switch, came back and picked up a cube, and then followed this really long and nice trajectory to the scale. And that's how they were able to get all of that during the autonomous period. So you can see as we watch videos of these games how much trajectory tracking can help get smooth autonomous modes. Let's look at some examples from this year's game. So by the way, the 2 robots that I showed you in 2017 and 2018, that's Team 254 from California. This is Team 1678. So how many trajectories do you think were in that full auto? So you saw the robot place 2 hatches. How many trajectories do you think it followed?
3.
3, exactly. So do you know what 3 they were?
Okay, so first one, they took the hatch, put it on the bottom, and it went back to get the other one and put it back on top. It's something like that, but I didn't like fully understand it.
Yeah, so we can actually count them up. So this is the first one. And now the second trajectory is to pick up the hatch panel. And finally the third trajectory is to place the hatch panel on the rocket. So let's take another look at another autonomous. So this is an autonomous that we actually ran. So we'll take a look. So can anyone tell me what happened in that video? What did our robot do? Yeah.
it put 2 hatches on the side.
Yep, and how many trajectories do you think there were there?
3.
Yep, so there were 3 trajectories. First one to place, and then the second one, which I have here, is to go back to the loading station. And then the third one was to place that. Now, how many teams in North Carolina do you think did some form of trajectory tracking during the autonomous period in 2019? What?
1.
Yeah, so there's not really a lot of teams in the state that have been using this technology, and you can see how advantageous it is to do something like this. We ran that exact auto during the playoffs of the state championships, and we were able to get huge advantages from placing the 2 hatches on the side of the cargo ship. So it's a really useful tool, and there are only a handful of teams across the world. Teams like 254 or 971 that have been able to do all of this. What do you think it takes to program that? How many lines of code do you think it is, or how many hours do you think we spent to write all of that? Anyone have any estimates or guesses on how long it took? Or how many lines of code do you think it was? Any guesses? It's fine even if it's not right. Yeah. 10 what?
like 10 lines code, I don't know.
Not quite. Anyone else? Yeah.
100.
Not quite. Yeah.
A lot.
I would describe it as a lot. So it's thousands and thousands of lines of code, and it took us 3 months in order to fully get all of this working. So we worked on it in the summer of 2018. So we actually ran some prototypes of our code at Thor in 2018, but really we got it working for the 2019 season. So it takes a lot of time and a lot of effort to get something like this working, and that's why there's not a lot of teams that can actually do this. But that all changes this year. So let's quickly talk about what we're actually doing. So at the end of the day, we need to send voltages to our motors. That's how we make the robot move. And all we have are encoder and gyro readings. So we have to somehow use the information from our encoders and our gyroscope, put it through some control algorithm, and finally get voltages for our motors. There's a series of control algorithms that we can use. So some of you might have heard of Ramsey or Pure Pursuit. And as I said earlier, until this year, teams had to implement all of this by themselves. They've had to write the thousands of lines of code to get from encoder and gyro readings to motor outputs. But that all changes in 2020. So a lot of developers, including me, looked at all of this and said, we need more teams to have access to things like this. So I actually started contributing to WPILIB in the summer of this year, and I helped contribute a lot of things. So I helped develop the kinematics, odometry, and trajectory generation code for this year. So let's talk about what's new. So we have a new command-based framework, so it's a lot cleaner this year. There's a new PID controller, so teams in the past have complained about it being hard to use, so it's a lot easier to use now. We have new kinematics and odometry classes. We'll talk about what that means in a few minutes. There's brand new trajectory generation code. So have any of you looked at path following before this year? Yeah, so what library did you use for?
Pathfinder.
Yeah, so a lot of teams in the past have used Pathfinder. And there's several disadvantages to Pathfinder, one of them being it takes really long to generate a trajectory on the robot. With the new trajectory generation classes, it takes about 5 milliseconds to generate on the RoboRio. So it's a lot faster, and it has a lot more features as well. There's an entire robot characterization tool. We'll talk about what that means as well. So let's talk about what you need, software and hardware-wise, to actually start tracking trajectories. You will need encoders and a gyro on your robot. You'll need encoders to measure the distance and velocity of each side of your robot, and you'll need a gyroscope to measure the angle of the robot. That is pretty much all the sensors that you need to track a trajectory. Let's talk about software. So you might not know what all of that is yet, but we'll get into it. You'll need to characterize your robot. You'll need to do kinematics and odometry. We'll talk about what that means. You actually have to generate the trajectory that you want to follow. And finally, you'll follow it with the Ramsey controller. So let's talk about how all of this works. You have your encoder and gyro readings, and this goes into odometry. So an example reading, let's say your left side is going at 1.7 meters per second, your right side is at 2.8 meters per second, and your robot angle is 10 degrees. And all of that goes into something called odometry. Does anyone know what odometry is? It sounds familiar to odometer, which is in your car. So based on that, can anyone take a guess as to what odometry is? Yeah.
Calculating where you are on the field.
Yeah, so odometry basically takes these measurements and calculates the robot's position on the field. So as you move your robot around, odometry can actually calculate your robot's position on the field. And we'll talk about how it does that. So odometry then takes your robot's position and gives it to the Ramsey controller. So here we have an example position, so 8, 4, 45 degrees. So we'll say that your robot is at 8 meters on the x-axis, 4 meters on the y-axis, and at 45 degrees. We give that information to the Ramsey controller. So the controller has information about the robot position. We want to track a trajectory. What's missing over here? It has the robot position. It doesn't have anything else. And we want to track a trajectory. What other information does it need?
Speed.
Speed of what?
The robot itself.
Well, yes, it needs the robot speed, and that technically comes from the robot. So the robot position is all the controller uses. So it uses the robot's position, but it actually needs the trajectory itself. So what the trajectory does is it gives the controller where you need to be. So for example, we need to be at 8.5 meters, 4.2 meters, and 50 degrees. And then the Ramsey controller looks at that and looks at the robot pose and says, we're at 8, 4, and 45, but we need to be at 8.5, 4.2, and 50. So what the controller does is it calculates some linear and angular velocity to actually get to where we need to be. So here it gave us 2.5 meters per second and 1 radian per second. Does anyone know what linear and angular velocities are? Any guesses? Okay, let's start with linear velocity. Do you know what linear velocity is?
Speed in a straight line.
Yep, so it's speed in a straight line. So if it says 2.5 meters per second, the robot will move 2.5 meters in 1 second. So it's basic speed. Angular velocity is the rate of change of the angle. So if I say, for example, 2 pi radians per second, what does that mean? So I'll give you a hint. 2 pi is the same as 1 rotation. So if I have 2 pi radians per second, what is the robot doing? Yeah, so it spins, and it spins 1 full rotation in 1 second because it's 1 rotation per second. So here, the controller says, you should move forward at 2.5 meters per second, and you should have an angular velocity of 1 radian per second. That means that we're moving forward while slightly curving to the left. Let's think of this in terms of the velocity of the left side of the robot and the right side of the robot. So if we're moving forward while curving to the left, which one should be higher, the right side or the left side? So we're moving forward and we're curving to the left.
Oh, the right side.
Yeah, so the right side velocity should be higher than the left side velocity in order to curve left. How do we actually calculate the left and the right velocities? That's what the kinematics classes do. So kinematics actually takes that value and it converts it into your left and right velocity. So here you can see that the right velocity is higher than the left velocity, and that makes it so that we can turn to the left. So these velocities actually go in to two separate things, let's say. First thing is robot characterization. What this does is it's a simple model. It can take this velocity, so let's say 1.8 meters per second, and it can roughly estimate what voltage we need to give to the motor to make it move at 1.8 meters per second. So for the 2.9 as well, we give their characterization. We'll say, I want the right side to move at 2.9 meters per second. Give me a rough estimate of the voltage that I need to give to the right motor. So that's what the robot characterization will do. The PID controller will correct for some minor disturbances. So the robot characterization estimate is rough. There will always be slight disturbances. And this PID controller will correct for those slight disturbances. In order to correct for that, it needs to get the current readings. So let's say we want to be at 1.8 and 2.9. We're actually at 1.7 and 2.8. So the PID controller will look at that and give us an output in order to get that velocity to match what we actually need to be at. And finally, it will send that voltage, and it gets voltages from the robot characterization. And finally, we pass those to the left and right motors. Does anyone have any questions about anything so far? All right, so we'll quickly talk about hardware. So we'll need encoders. You can use any type of encoder. So mag encoders are pretty common. You can use ones by US Digital. We're actually using Neos on our robots. So Neos have built-in encoders, so you can stick with those. You can use any gyroscope as well. So we have the NavX on our robot, but you can use things like the Pigeon or any analog devices gyroscope. So we'll quickly talk about what odometry is. So does anyone remember what odometry does? Yeah.
It calculates where you are.
Yeah, so it calculates the robot's position using encoder and gyro information. So let's say that square is our robot, and we move along that curve. How do we calculate the robot's position along that curve? What we can do is actually break up that curve into small vectors like that. And we can calculate the delta x and the delta y along each small vector, and then we can add all of those changes in order to get our robot's position. So that's what the classes are doing under the hood. Now, if you didn't have WPILIB, you would have to implement all of this math by yourself. It's a lot of trigonometry. But because you have WPILIB, you don't need to know how any of the math works. All you have to do is create a class and call that class. So, let's talk about kinematics. Does anyone remember what the kinematics classes do? Anyone remember? So we have linear and angular velocity. What does it convert linear and angular velocities to?
Voltages.
Not quite, yeah.
Each side of the drivetrain?
Yeah, so it converts the linear and angular velocity to the left and the right side. So in code, there's an object called chassis speeds, which is linear and angular velocity, and it converts it to differential drive wheel speed. So that's basically left and right velocities. So what we'll do now is we'll actually create these kinematics and odometry classes in our code. So we'll go back to our robot code. And we can actually create these classes. So the first thing we'll do is we'll create our kinematics class. So we can say differential drive kinematics, and we'll just call this kinematics equals new. So this actually takes in an argument called the track width. Does anyone know what track width refers to here?
How wide the robot is, or no, that's not it.
No, it is. It's the distance between the wheels of the robot. So in this robot, it turns out to be 28 inches. But the thing about all of these new classes is that they require SI units, which is meters. So what we can do is actually there's a new class called units. So we can use the units class to convert from inches to meters. So we can say units.inches to meters, and we can use our 28 value. Now let's create our odometry class. So we can say differential drive odometry equals new differential drive odometry. And the first argument is the kinematics. We just created the kinematics, so we can pass that in. And our second argument is our current robot heading. Now, did we create our gyro yet?
No.
No, so let's do that. So on this robot, I'm using the NavX gyroscope. So in code, that's referred to as AHRS. But depending on what gyroscope you're using, that class will be different. So we'll just call this gyro. And it's connected to the MXP port. And what we'll do is we'll write a quick method that actually returns our robot heading. So we will return it through a class called rotation 2D. So this represents a rotation on the field. So we can say rotation 2D, and we'll say get heading. And here we can return. So rotation 2D from degrees, all it does is it takes the degree value and stores it as a rotation. So here we can simply say gyro.getAngle. Now there's one slight issue with this, which is that gyroscopes in FRC return positive values as you turn clockwise. But if you remember from math class, in your unit circle, what happens to the angles as we turn clockwise? Does anyone know? Yeah.
They get smaller or negative.
Yeah, so they get more negative. So all of the geometry and the trajectory classes assume that as you turn counterclockwise, your angle gets larger, because that is how the unit circle works. So all we need to do to fix this is to put a negative value right there. Now we can simply call our getHeading method, and that is our kinematics and odometry classes. Now we've just created our classes, but are we updating our robot's position anywhere? Are we updating it? We just created the class. We're not actually updating our position yet. So what we'll do is we need to update our position periodically. And there's a method in every subsystem called periodic. So you can see that we've overridden that periodic method. And whatever you put in there will get executed periodically. So now what we can do is we can say odometry.update. The first argument is the heading, so we can get our heading. And the second argument is wheel speeds. How do we get the speed of our wheels? How do we measure? Yeah, so we use our encoders to measure that. So we'll come back to this, but we'll write another method, and it will return a differential drive wheel speeds. All this is the left side speed and the right side speed. So we'll say get speeds. And this will return our encoder speeds. So what we can say is return new differential drive wheel speeds. And we can say left master.getEncoder.get velocity and right master.getEncoder.get velocity. There's a little bit of a problem here. Does anyone know what the problem is? Yeah.
Well, the sparks are going to give you velocities in RPM instead of meters per second.
Yeah, so the sparks are going to give you, so we're using the Spark Max controllers, so they're going to give you velocity in RPM. We want to convert that to meters per second. So the RPM is actually RPM of the motor, but we first want to convert from RPM of the motor to RPM of the wheel, and then we can convert to meters per second. So how do we convert from RPM of the motor to RPM of the wheel?
Gear ratio?
Yeah.
Figure out the gear ratio.
Yeah, so we can use the gear ratio. So on this robot, the gear ratio is 7.29 to 1. So we can divide each one by 7.29. So now we have RPM of the wheel. How do we convert from RPM? Let's go to meters per minute. So rotations per minute to meters per minute. How do we do that? Yeah.
Figure out the wheel size.
Yeah, so our wheel radius in this case is 3 inches. So we can do times 2 pi r to get meters per minute. So we can do times 2 times math.pi times, because we're using meters for everything, I'm just going to convert this to meters. And now I can copy this. So now I have meters per minute. How do I get from meters per minute to meters per second. So that value is meters per minute. How do we get to meters per second? Anyone have any idea? So there's 60 seconds in a minute. Yeah, so you divide by 60. So from meters per second to meters per minute, or the other way around, you divide by 60. So now, that method,
The by 60 has to be outside.
oh yeah, I put it inside. So, now that method is returning our wheel speeds, and does anyone remember what unit? What unit are we returning our speeds in?
Meters per second.
Yeah, so we're returning our wheel speeds in meters per second. And now all we need to do is call that method. And now we're updating our robot's position. Are we storing the position anywhere yet? No, so let's create a variable to store our position. So the position is a pose 2D, which contains x, y, and heading. So we'll just call this pose. And all we need to do here is say pose equals. And now, periodically, so every 20 milliseconds, we are updating our robot's position as it moves around. So it gets our current heading, it gets our speeds, and using that, it calculates our robot's position. So now let's go back here. So if we come back to our diagram here, you can see that we're done with getting our encoder and gyro readings. We implemented our odometry, and we're done with our kinematics. So now, let's talk about the robot characterization. So the problem here is we have velocities. We want to convert them to voltages to give to the motor. Do you think there is a relationship between the speed and voltage? Is there a relationship? Yes. What do you think that relationship is? Is it linear, or is it exponential? Is it quadratic? Yeah.
Almost linear.
So it's almost linear. So there's a nice equation that we can actually use to find the voltage that we need. So it has 3 terms over here. You don't need to know how the math works again, because all of this is already in the code, but I'm just showing you all the math so that you can know what's happening behind the scenes, or if you want to implement this yourself. So the first term here is the static friction term. So if I have my robot here, and I give it 0.5 volts, will it move? Why not?
Well, it's really low. You gotta get a little more power to it. I mean, it might move, but like a little bit, probably.
So if we said that the relationship is linear, anything over 0 should make it move. But if I give it 0.5 volts now, it's not going to move. Why is that?
Friction.
Yeah, friction. So it needs there's a threshold voltage that you need to give it to overcome that static friction. And that is what that Ks value is. That is the voltage required to overcome static friction. And we're multiplying that by, so d dot is velocity. So we're multiplying that by a sign. So it's not the trigonometric sign, but it's just SIGN sign. So if d dot is positive, it will return 1. If d dot is negative, it will return -1. And this makes sense, because if our velocity, if we want to go in -3 meters per second, we don't want to give it a positive voltage. The next terms, so that is some constant times the velocity, and that is another constant times the acceleration. And when you add all of that together, you get the voltage that you need to give the motor. There is a convenient tool that we can use in order to find all 3 of those constants so that we can put them in our code. So let's actually find these constants. So there's a tool called the FRC characterization tool. I'll provide a link at the end of this presentation. So we'll open up that tool and I'll show you how it works. So here's the tool. It's a little small over there, but basically what you can do is you can select a project configuration. So we're using Neos. And then here you can select your motor ports and things like that. And once you select that, you can deploy that program to the robot. I can't do this right now because the tool currently doesn't support the beta image that we're running. So I have modified the robot program and I've deployed that already. What you can then do, once you've deployed the code, is you can launch a data logger. What this does is when you enable autonomous, it will slowly move the robot forward. As it moves the robot forward, it logs a bunch of encoder velocities and accelerations. And from this, it can calculate those parameters. So because there isn't much space to run the robot here, I've pre-run all of it and I've collected all of the data. So we can actually open the data analyzer and I can open up that data file. So it's in here. And I can click on Analyze Data. And you can see right there my KS, KV, and KA values. It can automatically calculate all of that for me. So you can see our KS is 0.268. So I lied earlier, you can move with 0.5 volts because the Neo motors usually have a lower KS value, but if you're using Sims or something like on our 2019 robot, that value was about 1.5. So that's just telling me that at 0.268 volts, I will be able to start moving. And then we have our KV and KA values. So what we can do now is actually use those values to create our model. So I can come back to our drivetrain. We're going to create a class called Simple Motor Feed Forward. So all this does is that it estimates the voltage needed given some velocity. So we'll say Simple Motor Feed Forward, and we'll just call this Feed Forward. And so this takes in the KS, KV, and KA parameters. So here I have 0.268. And then I have 1.89. And then I have 0.243. Yep, that looks right. So we've created our feed forward object. Let's really quickly just create a getter for that. So we can say public simple motor feed forward get. So we're just creating a method that will get the feed forward because we'll be calling all of these from outside of the drivetrain class. So let's go back to this. So can anyone summarize what robot characterization does in really basic terms? What do we just do, or what does the characterization do?
Finding the constants for your robot.
Yep, and what are those constants used for?
How much voltage you need to motor.
Yep, so those constants can be used, so this equation can be used to estimate the voltage that we need to go at a certain velocity and acceleration. And that key word right there is estimate, because it's just an estimation and there's always going to be some error. And we can correct that error using a PID controller. So this has three terms, the proportional, integral, and derivative. For a velocity controller, we can ignore the I and D terms and just focus on the P term. So what this does is it operates on something called error. So let's say we want to be going at 4.1 meters per second, but we're actually at 4 meters per second. So the error is 0.1 because it's 4.1 is where we want to be, 4 is where we are. So it's 4.1 minus 4, which is 0.1. The p-value is multiplied by that error, and that is the voltage that we add on to the motor. So here we have different p-values and different graphs of the voltage. So you can see that if the p-value is too high, we will oscillate around our set point. If the p-value is just right, we will reach our set point smoothly. So choosing the right p-value will mean that you will get to where you want to be as quickly as possible. In previous years, you have to find this p-value and tune it for hours and hours. But the characterization tool can actually give you a starting p-value that you can start with, and if that doesn't work, you can tweak it just a little bit. So we can go back to our characterization tool right here, and let's look at this side. So we'll select our units to be meters. I'll put in my wheel diameter, which is 0.152 meters. I've already done that calculation. For the settings preset, we can select WPILIB 2020 because that's what we are using. For a loop type, we are doing a velocity control. So we can select velocity. And all I need to do is click on calculate optimal controller gains. And that will give me a starting p-value. So you can actually start with that p-value and start tuning your robot. There's actually a slight bug with this tool right now, which will be fixed for kickoff. But the max controller output should be 12. So if I calculate, it'll just multiply that by 12. So I can use that value. So let's go back to our code and create the PID controllers. So we'll create a controller for each side of the robot. So there's one for the left side and one for the right side, because oftentimes we'll be giving the left side a different velocity than the right side. So we don't want to use the same controller for both. So we can say computer's not cooperating today. We'll wait for it. There we go. So we can say left PID controller equals new PID controller. And that value that the characterization tool gave us before was 9.95, so we'll use that. And we'll set the I and D terms to 0. And then we'll do the same for the right PID controller. And just like before, we'll create some getters for that because we'll be calling those. So we'll say get left PID controller. So now we've created our PID controller. So let's go back to this. So if we go back to the diagram from earlier, we have now finished robot characterization and PID controller. So all we need to do now is generate our trajectory and then use the Ramsey controller to follow it. So let's look at how to actually generate. So there's a tool called PathWeaver in WPILIB that you can use to generate trajectories like this. So I'll provide a link to PathWeaver at the end as well. So PathWeaver, so you can see I've generated a really simple trajectory right here. So you can use PathWeaver to generate something like this. PathWeaver will then export the trajectory so that you can import that into your robot code. That functionality is still in testing and I don't have that version yet. So we'll do the alternative and actually create the trajectory in our own code. But I'll show you how PathWeaver works as well. So we'll open up PathWeaver. Let's just close the characterization tool because we don't need it anymore. And then, so when you download the kickoff version of WPILIB, there will be desktop shortcuts for all of these programs. I'm just running it from the command line for now. So here we can create a new project, and we can select an output directory and a project directory. All of this hasn't been updated yet for the new WPILIB trajectories, but it will be by the time we get to kickoff. So for now, I'm just going to put some values in there. But all of this will be changed for kickoffs, and there will be a lot of documentation as to how to use all of this as well. So now we've created our project, we can create a path. So you can see that I have a path right here. So I can move around waypoints like that, and I can change the headings as well, and I can add more waypoints if I want to. So for example, we can recreate one of our auto paths that we ran, so it can look something like that. So when you create your trajectory, you will be able to export that and actually run that trajectory. Now, because we don't have a lot of space here, I have pre-generated a trajectory that will make the robot move here. But we'll just take a look at how to actually create the trajectory in our robot code, and then I can run that trajectory for you. So we can go back here, and if we go back to our robot container, we can create a method called getAutonomous_command. So the getAutonomous command will return a command that we will run for the autonomous period. So everything that we put in this command will be related to the autonomous that we're going to run. The first thing we want to do when creating a trajectory in your robot code is to create a config. So we'll create a trajectory config. And the config takes in two arguments, the max velocity and the max acceleration. Now remember that WPILIB uses SI units. So you can see right there, it wants it in meters per second and meters per second squared. So we'll use really conservative values because we don't want to break anything. So we'll say 2 feet per second. And even for the acceleration, we'll just do 2 feet per second squared. Now, for the config, we actually want to give the config our kinematics. What this will ensure is that around tight turns, Pathfinder had the issue that your right side or your left side wheel would actually go over your max velocity, but the new trajectories will actually slow down around the curves to make sure that the turning is smooth as well. Now, we haven't actually created a getter for kinematics, so we can go back to our drivetrain and create that getter. So we can say differential drive kinematics get kinematics, and we can return the kinematics. And here we can simply say config.set kinematics drive.get kinematics. So that is our config. Now let's create the actual trajectory itself. So we can say trajectory equals trajectory generator.generate. So the first argument is a list of our waypoints. So if we want to make a trajectory that moves 1 meter forward, we can say arrays.asList. So the first position is just 0, 0. So if you just create an empty pose 2D, it will be at 0, 0. And our next waypoint can be 1, 0, and then the new rotation 2D means that the angle is still 0. And then I can give it the config. So what this trajectory does is that it starts at 0, 0, goes to 1, 0, so that's essentially moving 1 meter forward, and we're giving it our config. So we've created the trajectory, we've done all of this. Does anyone know what the final step should be? So we've created everything. We just need to
Send it to the motors.
Yeah, we need to send it to the motors. We need to follow the trajectory. So there's a command called the Ramsey command, which the name comes from the Ramsey controller. We can use this command in order to actually follow our trajectory. So let's create this command. So we'll just call this command. Close new. So the first argument is the trajectory itself. Let's actually open this up. The second argument is the robot's position. Did we write a getter for the robot's position? When we created the odometry classes, remember that we were constantly updating the robot's position. So we can actually use that updated robot's position right here. So we can say drive.get. I guess I didn't create a getter for that, so we can do that. So we can say public pose duty get pose, and then we can return that position. So here we can actually then use that position. So drive get position. And if you're not familiar with this syntax, this is called a method reference. So it's a reference to the method. So as the command is updating in the background, it will be able to call that getPose method. So the next argument is the controller itself. So we can create our Ramsey controller. And this takes in two arguments. These are two tuning arguments. So what we found and what the documentation will recommend is that you use values of 2 and 0.7 because a lot of us developers have tested these constants and we found them to work pretty well. However, if you want to tweak them, you can read the documentation about what each constant does and see how that affects your trajectory tracking. The next argument is your feed forward. So we can go back to our robot container and we can say drive.get feed forward. The next argument is the kinematics. So we can say get kinematics. So you can see all of these getters that we wrote, they're all coming together now. Next we need our wheel speeds. So we have a method to do that as well. So we have get speeds. And then we need our two PID controllers. So we have get left PID controller. And we have get right PID controller. And finally, we need to give it a method so that it can actually set the motor outputs. We haven't written a method to actually set motor outputs yet. So let's actually write that. So we can write a method that says set output. And it will take in a left voltage and a right voltage. All we need to do here is SA.set left voltage. Now the spark controllers take in a value from -1 to 1, but voltages are -12 to 12. So how do we convert from volts to the percent? So if the method takes a value from -1 to 1, but my arguments are -12 to 12, how do I convert that? Yeah.
Divide by.
Yeah, so we divide by 12. And then for the right master, we do the same. Then we can come back here and give it that method. So we can say set output. And finally, we give it drive. And then we can return this command. Now we can go to our robot class and in autonomous init, so this runs once when we enable autonomous, we can say container get autonomous command .schedule. And one thing we need to put in autonomous periodic to make sure that our command is running periodically is the command scheduler.getInstance.run. So that's it. That's all the code that you need to track a trajectory. So all we did was write our drivetrain class. We put a few methods, kinematics, odometry, and things like that in there. We wrote a few getters, and then we created a Ramsey command. And that's it. So I actually have the same project, but with the actual trajectory that we're going to run here. So I'm going to get that set up really quickly. So I'll just, wait 1 second. I'll just get that up. So I can actually first connect to the robot, and then I can deploy the code. I don't know where that's coming from.
I think that's the Teams.
Yeah.
Just hang up.
Yeah. Anyway. So we'll deploy the robot program, and we will open up the driver station. And then we'll see if the program that we have actually tracks the trajectory. So I have a simple trajectory that will make the robot go in a circle. So I'll actually show you the waypoints for that as well really quickly. So you can see we start at 0, 0. We go 1 meter forward. And then we go to 2.3, 1.2. So that's a little more forward and to the left with an angle of 90 degrees. So what I'm going to do now is enable the robot in autonomous, and we'll see if there you go. So it went forward and turned 90 degrees, and it stopped. So you, we'll have to move it back, but yeah, I'll run it once more toward the end of the presentation. But you can see that that is a trajectory, and that's how you track trajectories using the 2020 software. So you can generate a long trajectory. So for in the 2018 game, you can generate a trajectory for the cross scale. These velocities and accelerations are really conservative because I don't want to break anything, but usually we would use something like 10 feet per second or something like that. And that's essentially how you follow trajectories using the new software. So I'll go back to our presentation over here, and I'll leave you with the resources. And that's it. So if you have any questions, you feel free to visit me up front over here. The code is all available over there. And yep, that's it. Thank you for coming.
So can you tell a little bit about 2020 library, when it will be available?
Oh yeah, so the library will be available a few hours before kickoff. All of the code is still public, but you can't run the code without the beta RoboRio image, which is what we are running. So if you sign up as a beta team, you'll have access to that. You can still copy the classes into your robot code and test them, but if you want to use the beta libraries, then you'll need the RoboRio image for that. So it'll be available on kickoff day, but all the documentation is already public, so that is the 4th link up there. Thank you for attending. That's it.